Hello everyone, a very good evening to all. Myself, Vivekananda Naik. I am a PhD research scholar in the Department of Energy Science and Engineering, IIT Delhi. I welcome you all once again for this ninth interaction session on the course Experimental Physics 1, which is being flowed by NPTEL in this July 2025 session with the course code NOC 25 PH 51. So today we will be solving a few problems that will be helpful for you in solving your assignment problems as well as for the problems that might come in your certification exam. So let's first discuss about the course content of week 9. So if we see the week 9 contents, so the lectures were about, so the first lecture was about determine the coefficient of thermal conductivity of a bad conductor. So how, so what is thermal conductivity, how it is determined, the coefficient of thermal conductivity of bad conductor, that were discussed. Then experiment related to electrical equivalent of heat, then specific heat of a given solid metal using Dulong-Petit's law, then determination of calibration curve of a given K-type thermocouple and determination of its Seebeck coefficient, and then lastly the theory regarding platinum resistance thermometer was also discussed as a part of the week 9 lectures. So before solving a few problems, let's first discuss the first concept, that is thermal conductivity of a conductor. So what is thermal conductivity? So thermal conductivity refers to the ability of a given material to conduct or transfer heat. So there are three ways in which there is transfer of heat: conduction, convection, and radiation. So conduction is the mode of transport of heat between solids, convection is in liquid, and radiation is in gaseous medium. So it is generally, so if you talk about thermal conductivity, the coefficient of thermal conductivity is given by K, and sometimes it is denoted by kappa. This is not K, this is kappa, and this is lambda. And similarly to the case of electrical conductivity, the reciprocal of electrical conductivity known as electrical resistivity. So similarly for thermal conductivity, the reciprocal is called as thermal resistivity. Now let's consider a case. So here you can see this in this figure. So there are two substances. This is at temperature T2, this is at temperature T1. So T2, this is the hot end and this is the cold end, and the condition is T2 is greater than T1, because so since the temperature gradient, since the temperature is larger in T2, so the heat will flow from higher temperature to low temperature, so heat will flow in this direction. And suppose this A is the cross sectional area through which heat is being conducted, and the distance between the two medium, that is one hot medium, another cold medium, or maybe two hot mediums with two different temperature, suppose the distance is D. Then if you talk about the amount of heat that is flowing, so this Q, it will be directly proportional to the area of cross section, directly proportional to the temperature difference, that is T1 minus T2 minus T1, and inversely proportional to distance T. So if you write it, there will be a proportionality constant. So Q is equals to K A T2 minus T1 divided by D. So this K is called as coefficient of thermal conductivity, and its reciprocal is called as coefficient of thermal resistivity. So now let's discuss a problem which is based on the concept of this thermal conductivity. Sorry, Now let's discuss a few problems. So this problem one is not based on the concept of thermal conductivity. There will be problems after solving a few problems which will be on that basis. But let's start solving the problems, and with as the session goes on, I will discuss a few more concepts related to the course content. Now question number one, what it says? It says a 4 degree Celsius rise in temperature is observed in a conductor by passing a current for a time t. When the double current is passed for same time through the conductor, then the rise in temperature will be ignore heat loss due to radiation. So we will ignore the heat loss due to radiation. So options are option A 8 degree Celsius, option B 16 degree Celsius, option C 20 degree Celsius, and option D 24 degree Celsius. So this is based on the concept of mechanical or electrical equivalent of heat. So let's first discuss the concept of joule heating. So when an electrical current pass through a conductor, so for example passes through a resistor, then the electrical energy is dissipated as heat due to resistance, because we know resistance is a result of collisions between the electrons when they travel. So that collision or that resistance leads to heating of that conductor when current passes through, because when current passes through the conductor there is flow of electrons. So when we are giving a particular force or external force we are applying to the electron, so they will start moving. So when they start moving they will collide more frequent, and then there will be resistance. So that is called as joule heating. If you discuss about the concept. So here let's consider a case when suppose this is a water is present in the beaker, this is a calorimeter cup, and there is a immersion heater, and we have the immersion heater, we are applying voltage across the immersion heater, and as a result a current passes through that heater. So when suppose what is the amount of heat that will be produced? So the joule heat, according to joule heating, the amount of heat produced will be I square RT, or we can say IR into RT. So V equals to IR, so VRT, or we can say sorry, let me, so it is IR into IT. So V is equals to IR, so VIT, or we can write VI is power, so P into T. So this is the power supply through which we are applying some voltage, and ammeter it is measuring the current passing through the heater, and voltmeter measures the voltage applied across the two terminals of the heater. So when the current passes through the heater, due to collisions, it gets heats up. So when the heater heats up, then the heat is applied to the surrounding, that is here. Since the heater is immersed in water, so water will be heated up. So due to the heat absorbed by water, the temperature of water increases. So here the electrical work is converted to equivalent heat in the experiment. So what is the amount of heat produced? So this H, we can say the amount of heat produced, W is equals to J into H, or we can say J is W by H, which is called as electrical or mechanical equivalent of heat. And if we want to know the value of J, so J is 4.186 joule per calorie. So 1 calorie of heat is equivalent to 4.186 joule of electrical energy. We know the unit of energy is joule and the unit of heat is calorie. So 1 calorie is 4.2 joule. So 1 calorie of heat is equivalent to 4.186, or if you take up to one significant figure after decimal point, so 4.2 joule of electrical energy. So based on this concept, let's solve the first problem. So the problem says a 4 degree centigrade rise in temperature is observed in a conductor by passing a current for a time t. When the double current is passed for the same time through the conductor, the rise in temperature will be, and in the bracket it is mentioned, ignore heat loss due to radiation. So we won't consider the heat loss, that is the amount of heat, that is um, the amount of heat produced in the conductor by passing current is directly absorbed, is completely absorbed by the sensing device which is sensing the rise in temperature, so there is no loss of heat. So the net change in, or the required amount of heat to rise the temperature to 4 degrees Celsius will be directly equal to the amount of heat produced due to the electrical current passing through that conductor. The options are 8 degrees Celsius, option B 16 degrees Celsius, option C 20 degrees Celsius, and option D 24 degrees Celsius. So I'll give you a few minutes to solve this question, and then we will discuss what will be the correct answer. So if we discuss, so just we discussed before a few minutes that the amount of heat energy produced when a current I is flowing through a conductor having resistance R and for a time t, given as Q is equals to I square RT. And since no loss of heat energy due to radiation, then, and this is the condition that there is no loss of heat energy due to radiation. Now if there is a 4 degree Celsius rise in temperature, then what is the amount of heat required for a delta T rise in temperature? So the amount of heat required for a delta T rise in temperature is given by the formula Q is equals to mc delta T, where m is the mass of that substance, c is the specific heat, and delta T is the change in temperature. Now see, in the question only the rise in temperature is given and for a time t is given, and there is no other information is given except the double current case in the second case. So now let's equate the two because there is no loss of heat energy through radiation. So the total amount of electrical heat energy will directly be converted to the amount of heat that is required to raise the temperature. So in that case it will be I square RT is equals to mc delta T, that implies delta T, that is the change in temperature, equals to I square RT divided by mc. So from this relation we can say the change in temperature is directly proportional to the square of current, provided that all the remaining things are constant. So now if we come to the question, then here there is 4 degrees Celsius rise in temperature for a current. Suppose the current is I. So case 1, I current passes through and temperature increases 4 degrees Celsius. Now if 2I current pass through, so since delta T is equal to I square, it will be 4 square, because sorry, so I current pass and it is 4 degrees Celsius, so it will be, so now, so when I current pass, then there is 4 degrees Celsius rise in temperature. So now we found delta T that proportional to I square. So when current is changed from I to 2I, then it will be delta T will be that proportional to delta T prime will be that proportional to 2I square. It implies 4I square. So it will be, so delta T prime will be 4 into delta T. So 4 into 4 degree Celsius, that is 16 degree Celsius. So the correct option is option B, that is 16 degrees. So when the current I was passing through the conductor, temperature I was 4 degree. So when current was doubled, then uh, square of 2, that is the temperature rise will be 4 times that of the initial case. So 4 into 4, it is 16 degrees Celsius. So I hope this is clear to everyone. Now let's move to question number 2. Question number 2 says a current of 2 ampere passing through a conductor produces 100 joule of heat in 10 seconds. The resistance of the conductor is, options are option A 2.5 ohm, option B 4 ohm, option C 5 ohm, and option D 8 ohm. So it is again similar to the previous concept that we are discussing. So a current of 2 ampere is passing through a conductor and it produces 100 joule of heat in 10 seconds, and we need to find out the resistance of the conductor. So I'll give you a few minutes to solve this question and then we will discuss. So again, we know the amount of heat produced in a current carrying conductor is given as H equals to I square RT, where I is the current, R is the resistance, and T is the time for which current is passing. So, what is the value of R? R will be H divided by I square T. H is 100 divided by I square 2 square into 10. So R equals to 100 divided by 40, that is 2.5 ohm. So the correct answer is 2.5 ohm. Now we move to question number 3. Question number 3 says, how many calories of heat will be produced approximately in a 420-watt electric heater in 5 minutes? Options are: option A 8 80,000 calorie, option B 60,000 calorie, option C 20,000 calorie, and option D 30,000 calorie. So here you should keep in mind that in the previous question, if you see, so in the previous question, if you see, the amount of heat that was produced was given in terms of joule. Here it was 100 joule, but here it is given as the all units are in calorie. So that you should always keep in mind what is the unit of heat that is given. So in according to the unit, we need to convert the uh, amount of heat by using the formula 1 calorie is 4.2 joule. So the question says, how many calories of heat will be produced approximately in a 420-watt electric heater in 5 minutes. So when a 420-watt electric heater it is running for 5 minutes, then what will be the amount of heat produced? So these are the four options. Again, this question is based on the concept of uh, joule heating. So I'll give you a few minutes to solve this question, and then we will discuss the correct answer. So let's solve this one. So we know H is given by I square RT, which can also be written as IR into IT, VIT, and VI is power, so P into T. So here it is given P is 420 watt and time it is given in minutes, so 5 minutes, which is equals to 5 into 60, 300 second. Now what will be the amount of heat? Then H will be 420 into 300. It is 6. This is 1,26,000 joule because it is watt into second. But we know 1 calorie is equals to 4.2 joule. So 1 joule is 1 by 4.2 calorie. So H will be 126,000 joule, which is equals to 126,000 divided by 4.2 calorie. That implies if you calculate it, it will come out to be 4.2, and this is 12.0, it is 3,000 calorie. So the correct option will be, sorry, this is 30,000. Correct option is option D, that is 30,000 calorie. Now we move to the concept of Dulong-Petit's law. So what it says, so the Dulong-Petit's law states that the product of specific heat and atomic mass or gram atomic mass heat capacity, so specific heat and heat capacity of an element is always a constant, and this is constant for all solid elements. So it is called as classical theory of Dulong-Petit's law. So the molar specific heat of many solid at room temperature is constant with value 3R. So this is the 3R value. As you can see, this is the Dulong-Petit's law, but in general the specific heat varies in this way for different metals, that has been shown in the figure. What is the value of this universal gas constant? This is R, which is 8.3144 meter square kg per second square into Kelvin into mole. And so now let's discuss a few things regarding thermocouple. So what is thermoelectric effect? So thermocouple operates on the basis of thermoelectric effect. So what is thermoelectric effect? So it is directly conversion of temperature difference to electric voltage and vice versa for a using a thermocouple. So a thermoelectric device creates a voltage when there is a temperature difference on each side. So when there is a temperature difference between the two ends, then a potential difference is developed. So or we can say when a potential difference is applied across the two ends, then the heat is transferred from one side to another side, which creates a temperature difference. So this thermoelectric effect, it encompasses three separately identified effects, that is Seebeck effect, Peltier effect, and Thomson effect. So what is Seebeck effect? Seebeck effect is the conversion of heat directly into electricity. Peltier effect is conversion of electricity into heating or cooling, and Thomson effect is temperature gradient when current flows through a single wire. So when current is flowing through a wire, then there will be temperature gradient. So that is explained in terms of thermoelectric effect. So now, since in our lectures, it was related to determination of Seebeck coefficient. So let's discuss more about Seebeck effect. So Seebeck effect is the electromotive force that developed across 2 points of an electrically conducting material when there is a temperature difference between them. The EMF which is developed is called as Seebeck EMF, or it is called as thermoelectric, thermal or thermoelectric EMF. The ratio between the EMF and the temperature is called temperature difference is called as Seebeck coefficient. Basically, it determines what will be the amount of EMF produced due to the temperature difference across the two terminals. Now, when a thermo how what for what thermocouple is used, it is used to determine the temperature of a system. So for one junction the temperature is known, and depending upon the voltage that is developed across thermocouple, we can know the temperature of the another medium. So it measures the difference in potential across a hot and cold end for two dissimilar materials, and this potential difference is proportional to the temperature difference between the hot and cold end. So this coefficient is called as delta V by delta T, that is the change in the EMF difference and the temperature difference. So what is the potential difference produced across the two terminals when the temperature difference is delta T? And the unit is microvolts per centigrade, volts per centigrade, but in generally very voltage produced or voltage different across two terminal is in microvolt unit. So it is generally the unit is microvolts per degree Celsius. So if S is positive, then the end with higher T has lower voltage, and if S is negative, then the end with lower T has lower voltage. So in general, the thermo EMF is given by this expression, and T is called as T P minus T reference. So these are the constants A, B, and C that depend upon the time of thermocouple. So there are different types of thermocouple. For example, in our course content, it was demonstrated for K-type thermocouple, and the values of A, B, C, D, they can be determined by calibrating it. So now let's solve a few problems that will be related to the concepts of thermocouple and Seebeck effect. So the question says the EMF in a thermoelectric circuit with one junction at 0 degree Celsius and another at T degree Celsius, it is given by E equals to AT minus BT square. The neutral temperature is, options are option A, B by A, option B, B by 2A, option C, A by 2B, and option D, AB. So here, this question, as I mentioned, it is based on the concept of thermocouple and Seebeck effect. So here it is given that the EMF in a thermoelectric circuit with one junction at 0 degree Celsius and other as T degree. So there are two junctions, hot junction and cold junction. So cold junction is at 0 degree centigrade and a hot junction is at T degree centigrade. Now the EMF that is produced is given by the expression E. So E is equals to AT minus B T square. So what will be the neutral temperature? The options are option A B by A, option B B by 2A, option C A by 2B, or option D AB. So these are the four options. I'll give you a few minutes to try this question, and then we will discuss what will be the correct option. So here the EMF expression is given as EMF equals to AT minus B T square. Now, what is neutral temperature? So, neutral temperature is the temperature of the hot junction at which the EMF becomes zero when the, so it is the temperature of the sorry the neutral temperature is the temperature at which the EMF is maximum. The temperature of inversion is the temperature of the hot junction at which the EMF becomes zero. So, what is neutral temperature? The temperature at which EMF is maximum. That implies dE by dt equals to 0 at T equals to Tn, that is neutral temperature. So E was AT minus B T square. That implies d by dt will be T, sorry, it will be A minus 2bt at neutral temperature when T equals to Tn, then d by dt equals to 0. That implies 0 equals to A minus 2b Tn, or Tn will be A by 2b. So sorry, here it is capital. So A by 2 capital B. So the correct option is option C, A by 2b. Now we move to question number 5. Question number 5 says the temperature of cold junction and neutral temperature of a thermocouple at 20 degrees Celsius and 280 degrees Celsius respectively, then the temperature of inversion is, options are option A 560 degrees Celsius, option B 540 degrees Celsius, option C 300 degrees Celsius, and option D 500 degrees Celsius. So these are the four options here. The temperature of cold junction and neutral temperature is given, so which is 20 degree and 280 degree, and the temperature of inversion we need to find out. So these are the four options. I'll give you a few minutes to try this question and then we'll discuss what will be the correct answer. So let's solve this one. So in the previous question, so in general the form of the EMF is given as AT minus BT square. So at neutral temperature we found it is A by 2B, where dE by dt was 0. And what is temperature of inversion? Temperature of inversion is the temperature at which EMF equals to 0. So that implies at T equals to Ti, E equals to 0. That implies ATi minus BTi square equals to 0. That implies Ti is A by B. Another Ti is 0, so which is we will not consider. So Ti is A by B. So Ti is A by B, Tn is A by 2B. So Ti is A by B, Tn is A by 2B. That implies Tn equals to Ti by 2, or Ti equals to 2Tn. Now this is valid when the cold junction is at temperature T equal to 0, but when Tc is not equal to 0, then Ti is 2Tn minus Tc, or we can say Ti minus Tn equals to Tn minus Tc. So Ti is 2Tn minus Tc. That implies Tn, it is given in the question as 280 degrees Celsius. Tc is at 20 degrees Celsius. So it is 2 into 280 minus 20. That implies 560 minus 20 equals to 540 degrees Celsius. And this is the correct answer. So the correct option is option B. Now we'll move to question number 6. Question number 6 says the thermo EMF in a thermocouple is given by E equals to alpha T minus half beta T square. If the temperature of cold junction is 0 degrees Celsius, then what is the temperature of inversion? Given alpha is 400 microvolt per degree Celsius and beta is 2 microvolt per degree Celsius. And the options are option A 220 degrees Celsius, option B 300 degrees Celsius, option C 400 degrees Celsius, and option D 600 degrees Celsius. So here the EMF as the form E is equals to alpha T minus half beta T square. Alpha value is given 400 microvolt per degree centigrade and beta is 2 microvolt per degree centigrade. And we need to find out the temperature of inversion, that is Ti when Tc is 0 degrees Celsius. So I'll give you a few minutes to think about this question and try to solve it. It is similar to the concept that we discussed in the problem a few minutes before, and then we will discuss what will be the correct answer. So if we solve it, so we know at temperature of inversion EMF is equals to 0. So E equals to alpha T minus half beta T square equals to 0. It implies alpha Ti minus is equals to half beta Ti square. That implies alpha equals to half beta Ti, or Ti is equals to 2 alpha by beta. So alpha is given as 400 microvolt per degree centigrade, beta is 2 microvolt per degree centigrade. That implies Ti is equals to 2 into 400 divided by 2 is 400 degree centigrade. So the temperature of inversion is 400 degree centigrade. Now we move to question number 7. Question number 7 says an immersion heater is rated 840 watt. It should heat 2 kg of water from 10 degrees Celsius to 40 degrees Celsius in about, options are option A 300 second, option B 150 second, option C 400 second, and option D 550 second. So again this is related to the Joule equivalent, concept of Joule equivalent of heat. So here the heater, the power wattage rating is 840 watt, and 2 kg of water we need to convert, we need to increase this temperature from 10 degrees Celsius to 40 degrees Celsius. So what will be the time taken? So we will use the concept of Joule heating. So the amount of heat required to increase the water temperature from 10 degrees Celsius to 40 degrees Celsius will be equal to the heat dissipated by the immersion heater, which is operating 840 watt, and then we can calculate the amount of time required for that event. So I'll give a few minutes and I'll be back in a few minutes, and we will be solving the problems, the remaining problems, and we'll look for the correct answer. So let's solve this one. So the amount of heat produced due to the Joule heating process is I square at T, or P into T, where P is power, that is 840 watt, and T is the time required. Now the amount of heat required to increase the temperature of 2 kg of water from 10 degrees Celsius to 40 degrees Celsius. We know Q is mc delta T, that m is 2 kilo into C is 1 for water, and delta T is 40 minus 10. So 30 into 2, that is 60. Sorry, this is calorie, not joule. So we will equate these two. So 840 into T is equals to 2 into 4200 into 40 minus 10. So this is 4.21 calories, 4.2 joule, and we converted to 2 kg is 2 into 1000 gram. So if we calculate, T will be, so this is 2 into 4200 into 30 divided by 840. So this will be, this is so 42 is 100 and this is 2, so 50. So 50 into 6, 600, sorry, 50 into 6, 300 second, 300 second. So the time required to heat the water, 2 kg of water, from 10 degrees Celsius to 40 degrees Celsius will be 300 second if we are immersing a heater of 840 watt in it. So the correct option is option A. Now we move to question number 8. So question number 8 says the heat is flowing through two cylindrical rods A and B of same material. The diameters of the rods are in the ratio 1 is to 2 and their lengths are in the ratio 2 is to 1. So if the temperature difference between their ends is the same, then the ratio of rate of flow of heat through A and B is, options are option A 1 is to 2, option B 2 is to 1, option C 1 is to 4, and option D 1 is to 8. So here it says heat is flowing through two cylindrical rods A and B. Suppose this is one rod, this is A, and this is B. So here, suppose so the diameters are in ratio 1. Suppose the diameter is D here, the diameter is 2D here, and the lengths are in the ratio 2 is to 1. So suppose this is 2L and this length is L. If the temperature difference between the end is the if temperature difference between the two end is same, so here suppose this is T2, this is T1, here also T2 T1, so T2 minus T1 same for A and B. Now we need to find out the ratio of rate of flow of heat. So we know the rate of flow of heat is given by Q, which is K A T2 minus T1, given that T2 is greater than T1, by L. So here L is the distance between the two ends, that is the length of the rod. Now here K will be same for A and B, because A and B are of same material. So A and B will be same. So now we need to find out what will be the ratio of the rate of flow through A and B. So what will be QA by QB, that we need to find. So I'll give you a few minutes and then we will discuss it to get the correct answer. So now let's solve this one. So K is same. So K is same, and temperature difference T2 minus T1, it is also same for A and B. So now what will be QA by QB? So QA by QB will be equals to AA by AB into LB by LA, because L was in the denominator. Now when the diameter are in the ratio 1 is to 2, area will be in the ratio 1 is to 4, because 1 square is to 2 square, because area is directly proportional to d square, is not it? So QA by QB will be equal to AA by AB into LB by LA. So AA by AB will be 1 by 4 into LB by LA 1 by 2, because the length LA by LB is 2 by 1. So LB by LA will be 1 by 2. So it will be 1 by 8. So QA is to QB is equals to 1 is to 8. So the correct option is option D. If this is clear to everyone, this is based on this formula. So K is same for both A and B because the material is same, and the temperature difference between the two end is same because it is written difference between the ends is same, but only change in their length and the diameter of the rods. So depending upon those factors, the rate of heat transfer will be different. Now let's move to question number 9. So question number 9 says the coefficient of thermal conductivity of a rod depends upon option A, temperature difference of two ends, option B, area of cross section of the rod, option C, material of the rod, and option D, length of the rod. So we just discussed when the material of the rod is same, then K is same, and the other quantities are variable, because the temperature difference between the two end, that will not depend upon the coefficient of so the coefficient of thermal conductivity, that won't depend upon the temperature difference, that won't depend upon the area, that won't depend upon the length of the rod. So all these three quantities, the rate of transfer of heat, that depends upon these three quantities, but sorry, this one, but the coefficient of thermal conductivity depends upon the material of the rod, because it is an intrinsic property of a material. It determines how effectively a material can conduct heat across its two ends, and the rate of conduction, that will depend upon the length of the rod, the temperature difference between the two ends, and the area of cross section through it which is conducting. So the correct option is option C. Now we move to question number 10. So question number 10 says Sorry. So let's move to question number 10. Question number 10 says two vessels of different materials are similar in size in every respect. The same quantity of ice of same initial temperature filled in between them gets melted in 30 minutes and 50 minutes. The ratio of their thermal conductivities will be, these are the options: option A 1 by 5, option B 5 by 3, option C 2 by 3, and option D 4 by 5. So what question says? Two bases of different materials. So A and B, they are of different material and similar in size. The same quantity of ice of same initial temperature filled with them gets melted in 30 minutes and 50 minutes. So ice amount is also same, and the temperature difference is also same for both the ice, for both the material vessels A and B. But the time difference between the time required for the ice to melt is different for A and B. So for A it is 30 minutes, for B it is 50 minutes. So again, since they are of different material, so the thermal conductivities of the two material will be different, and that will affect the time required to melt the same amount of ice, because they are of different material, so they have different thermal conductivity. So from this we need to find out what will be the ratio of their thermal conductivities. So let's find out. So we know what is the formula. So the conduction of heat, the rate of flow of heat from one end to another end is given as, suppose this is Q. Q is K A T2 minus T1 divided, so into T divided by L. So T, obviously the rate of heat, the total of, so so here Q star is the total heat flow. So Q is rate of flow of heat, but here Q star is the total heat flow. So we have multiplied T here. So since same amount of ice at same temperature melts, so Q is same for both containers, because same amount of ice, and also here it is mentioned same initial temperature. So the amount of heat required for both the cases is same, because the amount of ice is same and the initial temperature of the ice is same, and if it's getting melted, so the change in temperature is also same, or the final temperature is same. So but here, depending upon the value of thermal conductivity, the total amount of heat that will change. That's why the total time is different for both the case. So what will be the value? So we know Q1 equals to Q2. So Q1 is K1A T2 minus T1 into 30 divided by L equals to K2A T2 minus T1 into 50 divided by L. That implies K1 by K2 is equals to 50 by 30, that is 5 by 3, because these L are same, these are also same, and area of cross section is same because they are of same size. So same size means A same, so L is same, A is same. So K1 by K2 is equal to 5 by 3. This 5 is to 3. So the correct option will be option B, 5 by 3. So depending upon the time, depending upon the coefficient of thermal conductivity, the time required will be different because the amount of heat required for melting the same amount of ice is same. So depending upon the thermal conductivity coefficient, the required time will be different. So with this, we come to the end of today's interaction session. In the next interaction session, we will be solving a few problems that will be based on week 10 course contents. So that's it for my side for today. I hope these problems that I have solved and the concept covered in this week's lecture will help you to solve this year's assignment problem as well as the problems you may find in the certification exam. Thank you all.